Graphing reflections of functions. Ooh, look, pretty. So just a quick check-in. In Year 7, you really learnt about 3 different kinds of transformations. So can you remember them? Here's your original figure, T, and what happened to make the original one go to here with T dash? Hopefully you set a rotation, and it's rotating about C. You may have also used language like spin. Find T2. So this one here, how did this diagram transform into this diagram? Reflection. So it's actually reflected in the y-axis. We can reflect in the x-axis. We can also reflect through the line y equals x at different times too, but it's a reflection. I think in Year 7 you may have used mirror as well. The last one, T3, from T to T3, it's a translation. And basically it's just like somebody pushes it and slides it into a new position. So when we learned about transformations, we did translations, rotations, and reflections, and nothing else changes. So their lengths are all the same and their angles are all the same. So they're fixed in terms of their size, it's just that they've moved somewhere. In Year 11, or in the Year 11 preliminary course, we look at reflecting curves, and we'll reflect them a few different ways. So you can lean on your current knowledge of graphing too. If we had y equals x squared, you knew it was a parabola concave up. And then if you multiplied that by negative, you had the same graph, y equals negative x squared, just reflected through the line y equals 0, or the x-axis. So it's the same. We're just going to look at some more detailed curves really. And everything essentially that was negative reflects positive, and everything that was positive reflects and becomes negative. So a way to do that is to plot some key points. So if we look at this red graph and we look at graphing y equals f of negative x, the key points would have to be things like the x-intercepts, any y-intercept, which just happens to be 0, and this minimum point there that gets reflected up, and this maximum point up here gets reflected down. So you take the new places and you join them up with a curve. It's pretty easy. When we go ahead and reflect things horizontally, the way to achieve that, we haven't done a lot of yet. It's just the same, only we reflect them in the y-axis and not the x-axis. So again, we take key points and reflect them. The only current example I can think of is, so when we did things like y equals x cubed, we knew it went that way. But if we did, in brackets, negative x all cubed, it went this way and turned it around. So for example, if we take the red graph and we wish to reflect it through the y-axis, one way to do that is to use the graph and take key points again and shift them over. So the key points will still be those maximum and minimums, and they'll still be anything on the y-axis, anything on the x-axis, but also points we can read off the graph. So I'll show you what I mean. So the point here, negative 2, 0, will become 2, 0. The point here at 1, 0 will become negative 1, 0. This minimum that looks to be around a half, negative a third, will become negative a half, negative a third. This value is easy to read. It's 1, 1 or negative 1, 1. When it's reflected, it will become positive 1, 1. This value here is the local maximum there. It looks about, it's just after -1, say -1.2 perhaps. So we'll take it to where +1.2 is and add that in. So these are the new points that we will then join up to form a curve that's reflected in the y-axis. So a bit of a summary. It would be something definitely you should pause and record in your notes. But basically, if you're reflecting in the x-axis, your x value won't change. Your y value does though. It becomes the negative of it. So if I had AB, it's going to become A negative B. And that's reflected through this line here, which is the x-axis. So this point looks to be about 1, 2, 3, 4, 1 maybe becomes 4, -1, for example. One way to achieve that is to multiply the whole graph by -1. To flip things through the y-axis, the -1 doesn't come out the front, it actually comes inside. So by that I mean you're going to take, as I said, that AB, this coordinate AB, and it will become -AB because we're multiplying all the x's by -1. That's how we reflect lines through the y-axis. First example. The diagram below shows the graph of y equals f of x. It's the blue line. It's the top half of a sideways parabola. First up, let's practice stating the domain and range of y equals f of x. And then we're going to draw two sketches. One of the y equals -f of x and state the domain and range for that. And then we'll do the same for f of -x and state the domain and range for those. So for the first part, the domain, the x values starts at 0 and continues out to infinity and beyond. So the domain will be x with the square bracket through to infinity. The range is the same. It starts at 0 again, and it will effectively eventually get to infinity, just slower. So the range is as you can see. Now a thing to ponder is what happens to the domain and range if we multiply it through to multiply -f of x. We'll look at that. So for part B, we had to graph y equals -f of x. So if you recall, that's describing what kind of reflection. It'll be the reflection through the x-axis. So we will take key points and reflect them through the x-axis. So here we go. Here's some key points, 0, 0, 1, 1, looks to be about 3 and just under 2 and 4, 2. And they will be mirrored or reflected directly underneath where we found them originally. Then we join the dots. Clever, huh? Okay, for the domain and range now, why don't you have a try? The domain, it didn't change at all. The range, it did. It went from -infinity, so all the way down here now, up to 0. So the range was affected. For example C, you were asked to graph y equals negative, so f of -x. So then we are going to reflect this graph through the y-axis. So we will take key points again, but this time reflect them in the y-axis so the x values change. So let's look at some key points. Same ones as before, 0, 0, 1, 1. So 0 won't change, but the 1 becomes a negative 1 for point C, and so on. Then we join up our points that we've reflected in the y-axis and create the curve. No, so clever. Okay, so as I was saying, negative 1, 1, positive 1, 1 becomes negative 1. Positive 1, 2, 3, and just under 2 becomes negative 3 and just under 2. Positive 4 becomes negative 4, and then you join the dots. So what's been the surprise now? What's the domain and range for this new function? Because it was the x values that we were reflecting, it's the domain that gets impacted this time. It reverses around. The range we didn't touch, it's still going to be from 0 up to infinity and beyond. Example 2. Consider this different function, f4x minus x squared. And this time find the equation of and sketch the reflection across the x-axis first. Then find the equation of and sketch the reflection across the y-axis. And then we're going to do a double whammy and do both. All right, batter up. We are going to look at the reflection across the x-axis first. I'll call it g of x. So that means because we're going across the x-axis, we have to know we're multiplying the whole function by negative 1. We're turning it upside down, Ms. Brown. So when we multiply the function through by negative, that means you'll end up with negative 4x and positive x squared, which you can see I've rearranged into something sensible. Negative times 4 is negative 4x. Negative times the negative is positive x squared. Then we have to graph it. So it should be obvious. It's just a parabola. It has two x-intercepts at 0 and 4, and it's concave up. You could factorize that to check. So here's our solution, our negative of f of x, and here's our original function. So we can do it all algebraically, and it confirms what we were looking at with the graphs as well. 0 and 4, because when we factorize, we can find those x-intercepts. Concave up versus concave down, and these turning points are still on the axis of symmetry. Let's have a crack at B, or maybe you press pause and have a crack at B independently first. For B, find the equation of and sketch the reflection across the y-axis. So how do you reflect something through the y-axis? Yes, you multiply the negative inside the function this time. So let's see how we do that algebraically. It means replace x with negative x, doesn't it? So that's what that's going to look like. So 4 times negative x will be negative 4x. Negative x all squared is positive x. So we end up with this subtly changed equation. If we were to graph this, we could again factorize the x out and then find our x-intercepts. You could also find your axis of symmetry to find your vertex, and you'll get this. So we still have 0 and negative 4, and then 0 and positive 4. There's your original function. Here's our reflected function. Still concave down, because it was just reflected through there. It's like someone's folded the piece of paper through the y-axis. All right, now for the double whammy. So just keep in mind, this was our original function. If we reflect it through both axes, this is through the y-axis, then take this and reflect it through the x-axis. So I've got a really great idea what my picture is going to look like. It'll be coming this way, but how about the algebra? Let's have a look. All right, to reflect across both axes, that means we are going to multiply the whole function by negative f to get the vertically reflected function, and make the negative x go through for all the x values to get the reflection in the y-axis. Okay, algebraically, we can do this. The negative is still out the front. The negative x gets substituted all the way through. 4 times negative x is negative 4x. Multiplied by the negative, it'll be positive 4x. Negative x all squared is positive, but it's multiplied by the negative. So you have negative x squared, but you'll multiply that by the negative as well. So we will end up with 4x plus x squared. Factorizing that, the x out the front, then have 4 plus x, so the roots would be at 0 and negative 4. There they are, 0 and negative 4, and that's what we surmised was going to happen graphically before we even began. Do you think it would matter if we reflected vertically first and then horizontally? Doesn't look like it, does it? Question 3. A. The graph of y equals f of x is shown in red. Identify which transformation was applied to obtain the following. Right, so what have I done to produce this graph? Try and anticipate. What's happened here? What can you see? I hope you saw that it was reflected through the y-axis. So this minimum here at a half is still a minimum, but it's now negative a half. This maximum just past 1 is now over here, still just past 1, but the positive version rather than the negative. Let's try the next one. This time I am going to draw this function. What have I done to produce that? Can you see it was just turned upside down, Miss Brown? The local minimum became a local maximum at the same x value. The local maximum here became the local minimum at the same x value here. So the whole thing's just been turned upside down. So that means it's a negative f of x. Last one. It looks like this was turned upside down and something else has happened too. It's both. Can you see? This was turned up here and then flipped over the other side. So as I said, it won't matter if you even flip it this way. We'll start on this graph, I beg your pardon. Flip it this way first and then turn it upside down, or flip this and turn it sideways. The order won't matter.